All right, let's go ahead and get started. Apparently, my slideshow software is not working, so we're going to have to look at it like this.
Great.
I agree. Should we restart?
Try turning it off and on again.
Thanks, guys. Thanks a lot.
IT support 101.
Did you try reinstalling it?
The door is out there.
We don't reinstall it.
That would be annoying.
Okay.
Hey, he moved the camera.
So last time, what did we talk about last time? Oh, let's see if anyone remembers.
Circuits.
Kind of.
Flip-flops.
No, that was beforehand.
That was before.
No, after the flip-flops.
JK. I just remember flip-flops.
Trying to remember how to do everything.
Wait a minute.
I had a feeling
Last time we did the things.
I really did.
We did the stuff on the board.
Okay. Nice. Well put.
Hey, I said
What?
that first.
Truth tables.
Truth tables.
Yeah,
All
we
right.
did that too.
Why are truth tables so nice?
So it helps you figure out what you're doing.
Right. Okay. So we were coming up with basically a theoretical analysis of logic circuits, and we're trying to put them into different. Yeah. What was it? The sum of.
Oh. Sorry. No, I remember the and and the or symbols and
I remember some
decimal and
something else.
Minterms?
Sure.
yes.
Yes, the
Minterms and
minterms.
max terms.
And the max terms, right?
Sure.
Yeah. Yeah. See? She knows exactly what's going on. All right, so we learned minterms and max terms, but it made absolutely no sense why we were learning it.
Yep.
Today,
Yep.
we will actually figure out why we're learning it because it has to do with circuit optimization. And we're going to basically learn K-maps and how we actually optimize, or how Verilog will optimize your circuit for you. The point of this whole section, which is kind of a detour from computer architecture a little, it actually goes into digital logic, which is more of electrical engineering side, is at least give you an idea of what's going on in the back end and also at least explain to you why this is so difficult to do. So we are going to actually go through at least the basic optimization, which is with K-maps and I guess implicates as well. And then we'll finish up on this section. I'm going to give you homework on it, and then we're going to jump back more into a little more high level with architecture.
Oh my gosh.
Homework, yeah.
What?
We're reading about like another lab or homework?
No, it'll actually be, you have to use your hand and write things.
Wait, you're gonna grade us on?
Yes, I
Wait,
know.
we have to write stuff?
Can we
Okay,
type
actually you can
stuff?
type it up. I'm
Yeah.
kidding, you can type it. It's okay.
We're going that far from a computer?
All right, so last time,
Stone Age,
really,
man.
really far. We got to start.
Going back
I'm
to
gonna
the
make you
dark
breadboard
ages.
each transistor.
We'll find some spare wires.
Okay, good.
Take apart.
So last time we talked a little bit more about gates, Boolean equations, how we can move from our gates, which we talked about beforehand. How do we go from basically basic physics of silicon up to a transistor up to gates? And then we showed how they basically map to Boolean equations, which are actually pretty nice because theoretically they only have two values, 0 or 1. And we talked a little bit about the algebra and then of course standard forms. All right. Next, we're going to go into how we optimize it. We're going to talk about basically different types of optimizations. And then we're going to say that this is not a solvable problem, and instead we're going to do a suboptimal solution, which is espresso. Yeah, exactly.
Copy.
Now, we aren't going to do part 3, which is other types of gates and circuits. I think we can leave that for later because we really should get on to more architecture level endeavors. Keep in mind that if you ever want to go into digital logic, you're going to be looking more into stuff like this and breadboarding and how gates are put together. But if you don't care about that stuff, that's actually just fine. You just need to understand what's going on. Okay, so optimization. We have a circuit, we can describe it. Hopefully is at least intuitive that when you write code or when you write Verilog, you're not necessarily giving it the most optimal solution to a problem. Everyone good with that? Just like we can. So we want to find out, well, first off, maybe you did give us the optimal solution. How can we confirm that? And then if not, how can we determine whether one solution is more optimal than another? And we have different ways of costs, or we evaluate it based on the cost. There's the literal cost, which is how many literals are being used, gate input cost, how many gates must go in, and then basically gate input cost with knots. So let me first show exactly what that is, and then we'll go into it. Wow, I fixed the slide, and it still does this.
Oh my gosh.
That's really.
I don't even know.
I fixed it. All right.
Are you sure?
Oh, I did.
I think
Where does anything belong?
D not supposed to be the B.
So hold on. These 3 guys are down here. These 4 guys are over here. And then these 2 guys, this is so dumb, right there, and then over here. Wow, this is terrible. I fixed it this morning, too. All right, so what's the literal cost? If everyone can pretend to read this, it's literally the number of literals. Okay,
Woo!
look, you count. 1, 2, 3, 4, 5, 6, oh, I'm sorry, 6, 7, 8, and there's 8. This is even more hard. Going to be moving on. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that one's going to be 10. Can anyone
Or
try?
Is it 11 because that C up there? The C not up there on the side?
Yeah, there's a C knot. Oh yeah, 11. Thank you. A, B, C knot. All right.
Just
And
to
then
make
what's the
sure.
last one?
Really? Is it long because you'd have to like, do you have to like kind of multiply it out, or is it just count up inside?
Just count the number of literals.
Okay. I got 10.
I got. What did everyone else get?
Right. We're counting with 3 above.
Is it that bad, Matt?
And we're
This-
just Sydney.
All right. I got 10 as well.
10. I see 10.
It's okay.
Oh.
You don't
I
count
see
the L.
8.
Yeah.
You see
No.
8? All right. So the question is,
Oh,
which
yeah.
solution is best?
8.
The least amount.
8. So it would seem that 8 would be the best for now, at least with the literal count.
Right.
But of course, there's other things that we need to look into, which may add to it. There's the gate. Wow, I fixed this one as well.
Let's just assume
Oh god.
for now that anything you fixed is now no longer fixed.
Yeah, apparently it's not going to work. Don't worry, it gets better later on the slide. And I do mean that in the literal sense, not the
Oh,
sarcastic
like,
sense.
oh. I assume sarcasm.
That was
I
not
did too.
sarcasm. All right.
But wait, there's more.
So gate input cost, number of inputs to gates, corresponds to a given number of equations. Right. So the point of this is you have to also take into account while there's certain literals coming in, you may also have interaction between different gates that you have to account for as well. And that can be a cost. Really, this will make more sense when we get to a picture. Since these slides are messed up, we're going to skip it. Here we go. All right.
The last one.
Now, how many literals are there here?
5.
Yeah, I got 5 as well. Oh, see, that made it easy. See, 5
I
literals.
just counted the letters.
Yeah, I know that.
Yeah, I just counted it in the whole, yeah.
And then
equation
things were
thing.
just happy. Okay.
Now, if you didn't have the letters.
Ooh.
Bum, bum, bum.
Whoops. How many
Whoa.
gate? All right, we'll go ahead and add the gate inputs. There's 2 extra gate inputs because if you notice, while these 2 ands are up here, you still have to have another input cost going to the final OR. So the gate input cost is actually your number of literals plus any additional gate inputs you need to account for.
2.
Right, so there'd be 2 extra gate well, there's 2 extra gate inputs above the literals, is what this is showing. All the literals are still gate inputs because they're going to a gate. It's just you have 2 extra ones that this is trying to show that may come up. So the gate input cost is generally at least your literal cost.
If not, then.
Whoops. And then the gate knot you actually add for each knot as well that you have inside the system. The reason why gate and gate knot are usually separate is in general knotting something is actually pretty quick. So sometimes it's negligible what the knot is and other times it's actually very important. Okay, so do we want to minimize these or maximize these?
Minimize.
Minimize, all right, good. We want to make this as small as possible. Oh good, these were not messed up. I know, right?
Whoa. It's a miracle.
So the top one, literal of 6. 1, 2, 3, 4, 5, 6. Everyone good? So the gate has 2 extras. Why is the gate cost 2 more than the literal?
Because
There's two
there's 2 gates that go into the final OR.
Right, so there's 2 inputs to the final OR that aren't coming directly from a literal, they're coming from another gate. All right. And then gate not's another +3 because there's 3 knots up on the board. All right. So down here, the literal cost is now 6, still the same. The gate cost is 9. That might be hard to, well, no, it's
Yeah,
not.
because there's 3
Yeah,
wires.
3.
Yeah.
There's 3 right there. And then the gate knot is now 12. Same function and same literal cost. We could show that mathematically, or you can just trust me for that.
Sure.
Thanks! Obviously, the first one has a better gate input count and better gate input count with knots, so we select it because it's going to consume less area as well. Although, which one of these has the same performance cost?
Literal.
Performance time, I'm sorry, time or saturation cost. That is a trick question.
Are they all the same?
Yeah, they're both the same here.
Yeah.
So the saturation or the time that it takes for these circuits to complete is going to be the same, but the bottom one consumes less area, which is better, so we'd want to select the bottom one.
It consumes less
You mean
area, but it
I don't
looks
understand,
so
Facers. You got it.
So the bottom one consumes less area?
The top one consumes less area. Did I say bottom?
You
Yeah,
said
yeah.
bottom one.
Whew, that was bad.
Dr. West.
I was like, there's
Dr. West
extra
is
stuff
lying
all
today.
over the place.
No, the top one's better.
Did you have your tea this morning?
No, not all of it. That's my problem. I should probably go get it. All right, so we want to minimize the gate input cost. All right, great. We could use Boolean algebra to do this. All in favor?
Sure.
Oh, we got 2 people. All right.
I didn't do it. It was Caitlin.
Speaking for the whole back row,
Oh, you
not here.
not here? You do it? Okay.
Hey,
Sure.
give Jonah about another 20 more minutes. And
Mm-hmm.
he'll pop up.
Wow.
Sad but true.
All right. But it would be nice if we could have the computer automate this, right? Yes.
Yeah.
Unfortunately, getting a computer to do Boolean algebra is not exactly a efficient task. So,
Yet.
yeah, well, sure. Sure.
Ever.
At least with current machines. So how do we reduce it? Well, we can treat everything as a 2-level function, aka a sum of products or a product of sums. Hey, remember that? And then we can introduce a graphical technique using, let's see if I pronounce that, Karna? K-maps, whatever. They're called K-maps. So K-map is a collection of squares. Wow, really? Okay, can we just go to the picture?
Nope.
Here's a K-map. Good. Oh.
Whoa.
Okay, so for a K-map is going to be different for the number of variables. This one is a 2-variable one. You have, of course, y on the one. Y is currently on those 2 columns. X is on those 2 rows. And each square is going to delineate, in this case, the minterm, which remember was the product of 2 variables. So the minterm of 0, do y'all remember what that is with 2 variables? Good morning. We'll go over here. Oh, wow, this thing is gone.
Yeah.
I am not going to get that. Oh, so close.
Yet so far.
Thank you, John.
This close only counts in horseshoes and handguns.
So, what was a little m if we had 2 variables here? I'll give you the first one. X naught, y naught.
Oh.
Sure.
Okay? How about for this one?
Yeah, X. Why not? Is that right?
X
Other
not-
way.
X
Not
not
Y?
Yeah, there we go. Because the bit that's on tells you what is normal and not complemented. So then 2 is
X.
X,
X.
Y not.
x, y naught.
Yeah.
And then
Yeah,
X,
X,
Y.
Y.
There we go.
Oh, we start with X.
We're good.
Slowly.
Okay. So on the left you have x, 0, and 1. And then y, 0, and 1, aka the bits, just like over here on the board. And then you would fill in the blocks for which minterms are being used. And as we showed last class, all functions, or all, I'm sorry, circuits can be expressed as a sum of min-terms, or a product of max terms, but we're going to stick with min-terms for now, because it's going to end up being very nice. Let's see. And for our 2 variable, it's going to go 0, 1, 2, 3. And hopefully that's somewhat intuitive by the way it looks. Because it's 0, 0, 0, 1, 1, 0, 1, 1. All right. Things are going to start getting a little confusing soon. Are you ready? Okay, good. We're going to show more first.
Yeah. That's nice.
A K-map is just a way of showing a truth table, kind of a shorthand way, which is nice. For example, we choose A, B, C, D from the set 0, 1, just pretending it's the answers. Okay, then it's the same thing. What's on the left is the same thing as what's on the right from the truth table. Okay? Now, I'm going to go write this on the board. So this is really X naught, Y naught. This is really X, Y naught, and this is really,
I mean, X naught, Y.
X naught, Y. This is X, Y naught, and this is just X, Y.
You're right, it got confusing.
Yeah, it did. See? I told you.
Good.
So the point is, if this is a 0, that's a 1, that's a 0, and that's a 1, what's our function? Well, it'd be X naught, Y, or X, Y, which happens to be what? Oh wait, do you see how I went from this to that? Because if there's a 0, then you don't use that min term. If there's a 1, you use that min term.
Mm-hmm.
So in this case, I would use these two and OR them together. Okay? So do you see how I went from this to that?
Mm-hmm.
Yeah.
Yes?
That
No,
part, where'd the zeros and ones come from?
I made them up.
Oh, okay.
I made up the zeros and ones as an example.
Okay.
Okay? The zeros and ones are made up by me, just to show you how I could go from here to there.
Okay.
Okay? Good. So then, if the 2 ones are here, it's X naught Y or XY, which happens to be what?
Y.
Y. Which, if you notice, are just the 2 columns under Y equals 1. That's a preview of what's about ready to come.
Yeah.
I like puzzles.
How do you get the order? What was that?
The OR. So these are min terms.
Yeah.
When you combine min terms, you OR them.
Okay, yeah.
If we were combining max terms, we'd be ANDing them.
Yeah.
That's annoying.
You're annoying.
Oh, the love. Okay. Oh, hey, look, we're going to do another example on the board.
Yay.
So it's the same thing, just a little different. For example, f of xy equals x. You filled this out with the K-map. You'd put 1s where x is 1 because it's x. And then when x is 0, you put 0s. Which would end up, when you copy it, remember this one down here is x, y naught, and this one is xy. So you OR them, which happens to just be x again. All right?
Yeah.
All right. Simple example. Slightly more complicated, x or y. Why are you in parentheses? Oh, I see. Never mind. It's confusing that they did it with the parentheses here, but again, if I were to write this on the board, this is x naught, y naught. This is x naught, y. And this, of course, is x, y naught. And this is x, y. So it's the OR of these 3 terms. They decide to do these 2 and then those 2 and then OR them together. I think it's a little more confusing, but still okay. So if we were to do it my way, we would have x naught y or x y naught or x y.
Yeah.
Mm-hmm. Oh yes. If I were to, I could take one of these, maybe these 2 guys, and take out the y, and then that would just have the y. And then by the subsume
So we just have like one.
theorem, it would change. You could also get the other one to be x. Yeah. Yes.
So you're just oring the ones that have one.
Yes. That's all you're doing. That's it. Okay.
Wait, so when you're like canceling everything out and simplifying it and all that, is the answer 1 or is it x or y?
The answer is this
Okay.
at the end. Well, the first answer is this guy. The final answer would be x or y.
Mm-hmm.
Or just, I'm trying to show you that these two are similar. This is how you go from the K-map over here, because we talked about last time about how all circuits can go to a sum of minterms, which is this form. And then I'm showing you how all sum of minterms can be shown as a K-map. And then eventually I'm going to show you how a K-map can be used to get an optimal circuit.
Well, that's why I just wasn't sure if you were able to simplify 2 out of those 3 minterms together and then
Yes, you
simplify
can. You can. Because if you were actually looking at this, another way to look at it is it's really these 2 boxes or these 2 boxes, which is just x or y, aka what we had to begin with.
So
But if you're just-
that's why it's in parentheses and that's why there's a duplicate.
Yeah, they duplicated it because, they wrote each one out.
Okay.
They did.
I think that's why I was getting confused, is when I was comparing it, I thought it was just the 3, and so you compare
It is just the 3. But you could think of it, that's the point here. You could think of it as 3 individual ones, or you could think of it as these 2 or these 2.
Well, I
It's the
think
same
I was
thing.
thinking of it as the bottom 2, and then you take the simplification of that and compare it to the 1, not compare these 2 and then compare the other 2, and then it's a combination of those.
What you're the good thing you're looking at is the fact that there's a lot of different ways to look at the K-map, which is what's important here. Yes, PJ.
On the last one, you only ORed x naught y and xy. And on this one, you ORed 3 of them.
Right, because there's 3 ones.
Okay. So the 1 means...
One means you can think of it as that's the coefficient in front of this term.
Okay. Oh, okay.
Right. Yeah. So if it's 0, obviously it's gone.
But how do we simplify from x naught y plus x y naught plus x y to
So-
x bar y?
Using Boolean algebra last time, I could go through all the steps. It would come back out to x or y. But I'm going to show you how that's not necessary anymore in a bit. Let me erase this first. But before I show you how that's not necessary, we're going to go into 3. Okay, let's go into 3 variable. 3 variable is going to start looking a little more confusing. It's actually going to be somewhat way more confusing because of the way it's laid out. Notice up top we're going to have y and z, but we're going to combine them in a certain way, and this is just to make it so that the K-map is going to work out well. But notice we go from 0, 1, then 3, and then 2. Just trust me for now, okay? It'll make sense why we do this in a bit. And then we go 4, 5, and then we flip the 7 and the 6. So if you look at the terms, that's what they would be on the bottom.
Is it because 1 1 is like
Yeah, it's
does it
switched.
break stuff?
The only way I can intuitively tell you why we're doing this at this point is notice that each time you go over by 1, you're only flipping 1 bit. So you flip that guy on. You can't just flip 2 bits. So you're just going to flip the other one on and then flip the other guy off.
Oh, okay.
That sounded like something bad. But anyways, same thing going
Yeah,
down.
flip 2 of them off.
Only 1.
All right.
Gotta pick and choose. Pretend you got them.
So that's what's going on here, what they're doing. All right. So let's see if they give us a good example. There's different ways to look at it. Alternate labelings. I think this label on the bottom is going to make the most sense because you have x naught and x, you have y naught and y, and then you have z and z naught. And that really helps you understand what exactly is being labeled inside of each box. So, if you remember, if you have the 3 bits, this one is x, this one is y, and this one is z. So obviously right here it's got to be the naught of all of them. So there it is. When you go over by 1,
Z's
That's the
on.
Z, so Z's got to be over here. And then when you go over another one, then Y finally shows up as well as the last one. So the last two columns being Y makes sense. But then that last one, of course, the Z goes away. And then the middle, the Z comes
I get it now.
All right? You get it. Good. Any other confusion? I think this is very
It
confusing.
looks confusion, but I get it.
All right. So some more example functions. We show that you can just write it as a sum of min terms. So if we just write 2, 3, 4, 5, we can write them in right here. So let's see. Read off to me what this would be.
0, 1, 1. So it would be
Oh, give me
X
the
naught,
midterm.
Y, Z.
X naught, Y, Z, or
X naught, Y, Z naught.
yep.
Then X, Y naught, Z naught.
So we got X, Y naught, Z naught. Okay.
Then you got X, Y naught, Z.
Okay. Here's where the tricks start coming into. You can actually read these in 2 blocks at once if you want to.
Whoa.
Because if you look at this, you don't need that Z,
Right.
right?
Right.
So you can just read this as XY.
right.
I'm going to do this. And, well, I'll put 1 equal sign just to make this some way. So this is really just X naught Y. Or, and then what can you just read this guy as? Well, he's X and Y naught. Right? Don't care about the Z, because you got
yeah.
both the Z's in there, so you don't care about the Z. It's just X and Y naught.
Is this just gonna end up being like 1?
Yep.
Not necessarily.
Because you
Yeah.
got X naught and X, and you got Y and Y naught.
Well, let's see. If they are both 1, then this would be 0 and that would be 0.
Okay.
But yeah, that would be the minimum of that K-map.
So you can't make it any smaller.
Correct. Okay. All right. Let's. No, this one's gonna be. I don't have room for this. How about this guy over here? We'll do it right over here.
But X naught Z Y.
X naught, Y Z.
Y Z.
Yeah. Or
X, Y naught, Z naught.
okay.
Or
X Y
X,
Z.
Y, Z.
You're not gonna need the Z.
Yeah, but do we need that?
You're not
Nope.
gonna need the Z.
Just X Y.
There we go. Now see what I did there?
Yes.
Yee.
So we can just take those two and ignore the Z naught because they're the Z and Z naught because that's already included in those two.
Can we ignore the first 2 as well then? Because it's X naught, Y, Z, and X, Y naught, Z naught? And it would just be X, Y, or no?
And that would be which one would that be?
The first 2?
No,
3 and
because,
4?
well, what would you take out? Because you got X naught here and then you got regular X down here.
Oh, it has to be the same term?
The only reason why those two combine mathematically,
There he is.
you were off by 15 minutes.
Yeah, I know.
So if you look at these two guys over here,
Okay.
this is really just X, Y, Z, and this is
X,
X,
Y, Z naught.
Y, Z naught.
Okay, so it has to have 2
Right, you
similar
can take the
terms.
X, Y's out and then have the Z, and that's why you can combine those two
Okay.
mathematically. But pictorially,
can't do that,
you can
right.
see that both Z and Z naught are added there, so you're fine.
Okay.
All right. Everyone following so far? We're going to go over this again, don't worry.
So you said it becomes confusing. When does that happen?
I think the 4 variables when it gets confusing.
Gross.
Hey, we could do 5 variable if you want, but then only sadness occurs.
Only 7.
Oh yeah, it's only 5 variables were sad. Yeah, I'm like, I don't know how to draw this anymore.
It just starts getting
It
ridiculous.
just
and
get,
then
it's like trying to draw a
everybody's
3D
not
object and you can kind of do it, and then like, all right, let's go to 4D. Yeah,
happy.
right.
Okay.
Which I can do.
don't
I can do a
understand
40
why you would
cube
draw
for
4D.
that, but it's really weird looking.
It's not.
All right, by combining squares, we can reduce the number of literal costs.
Hard enough to draw 3D.
So if you think about, go back to your 3-variable K-map. Let me draw that over here.
Yeah.
Actually, how did we do it? That didn't make
X
didn't
naughts
make-
on top.
Yeah, X naughts on top. And then we had Y over here, didn't we? And Y naught. Yeah. Then we had Z right here, and then
See that on both sides.
yeah. And then we did this number.
Yeah.
Good.
It's beautiful.
It is beautiful. All right, so 1 square represents the min term with 3 variables. I don't know why they call it a square when obviously it's a rectangle, but anyways,
2 squares together.
but it's 1 square. 2 adjacent squares represent the product of 2 variables. Okay, what does it mean by that?
Oh, it's saying the individual
Oh yeah,
squares
it's saying the
and-
individual pieces of the rectangle are squares.
Oh, I'm sorry, yes. The individual one's 3 variables. Thank you.
There we
I got it
go.
backwards. And then right, so each square represents the 3 min terms, because right here you have X naught, Y naught, Z naught, so that'd be 3 terms.
Mm-hmm.
2 adjacent square represents the product with 2 variables. So if you were to add this guy in here, you get X naught, Y naught, Z. Obviously,
Then
we
it
don't
would be
need the
X
Z,
naught,
so
Y
we
naught.
could drop it. 4 adjacent represents a product term with 1 variable. Okay,
So if you did
there's, yeah,
top
now,
row.
there's there's row and there's column
Column.
here. So you could go out here and do, well, we got X naught, Y, Z, and then X naught, Y, Z naught. And if you look here, that's just X,
X naught.
or X naught, thank you. Down here, you can do X, Y naught, Z naught, and then down here we have X, Y naught, Z. So then these 4 guys would be what?
Why not?
Why not?
Y naught.
Sounds like a
Why not?
Pokemon.
Why not?
Yeah.
Why not is a Pokemon.
That's why it
There's
sounded like one.
So the X naughts, and then the X is down below.
Because it has X naught, and then it has all the other possible combinations of the other 2 variables. So if you're going to OR them all, you can take, if you were to OR all 3 of these, X naught, Y naught, Z naught, or X naught, Y naught, Z, or X naught, Y, Z, or X naught, Y, Z naught, you could take the X naught out, right? Because they're in each term. So we'd have X naught, then you'd have Y naught, Z naught, or Y naught, Z, or Y, Z, or Y, Z naught. This is every possible ORing combination, right? So this has to be 1. And then you just have X naught. Same thing happens when you have these 4 together because they're adjacent, and that would then be Y naught. Because that's what you can take out of all 4 of them.
I just kind of think of like.
So on the top row, X naught is the only thing that stays the same, and then the square of all 4 to the left, Y naught is the only thing that stays the same.
That's correct.
So basically, if you look at your labeling, and you say, okay, I'm taking all 4 blocks in my Y naught area, then it's Y naught. If I'm taking.
Yeah, exactly.
If I'm taking all the blocks that make up that, then I'm
Yeah. Same thing, if I were to choose these 4 right here in the middle, what would it be?
Z.
Z. If I were to choose the 4 on the or the 2 edges, what would it be?
Z naught.
Z naught. You see that? So this is actually a square right here. It does wrap around. Because you could also do, well, I mean, yeah, you could do the square going up like right here, but then that's just Z, so we're good. Okay. If you were to put 1 in each of these blocks, what's the answer? The circuit is always on or 1 because you've just filled in every possible combination.
Tautology.
Yeah, it's a
Yeah.
tautology. There you go.
It's impractical.
Nice. Okay,
Thank you.
here's another example they did through slides.
Yay.
Slides do a lot of things.
So notice that Y is turned, all the Y's are turned on and all the Y naughts are turned off. So looking at the picture, obviously the answer is Y. You could go ahead and do it all out if you want to, but whatever. Okay, so now you can do, Well, let's go and do this example. What's this one?
So we X naught, Y naught, Z naught.
All right, make it simpler.
So.
Okay.
X naught, right?
X naught, Y
X
naught.
naught. X naught.
X naught, Y. And
X naught, Y naught.
Yeah, X naught, Y.
Or YZ.
Yeah.
So then just X naught or Z.
Uh,
Right. Could you
I'm
reduce
just
that
doing
down?
the two.
oh, could we reduce this down even more?
Could you take out the Y's or no?
No, this is a Y naught.
No. I didn't know if they'd cancel the Y naught and Y.
No.
Okay. Yeah.
Yeah. All right. See how that was quicker? Or now it's a little quicker to read. You have this guy and then you have that guy. All right. Oh, we're gonna add another one.
Oh yes.
What was that last one? You want to see that? I'll do it again. Yeah. Yep, because we got the Y and the Y not in there. So we don't need those. All right, let's try it again.
Oh, yay.
So is this one going to do the animation
Why
for
not
me?
Z?
Yeah, it is. All right, so that first one,
Why not?
that's correct. Yep.
C.
Or a Z. Okay. Oh, we're doing another one.
Z naught.
Oh, this kind of doesn't that just highlight the mall? Okay, all right. fine.
Every square.
So it's Y naught.
Exactly. All right, guys, good job. All right. So, if you were to, hopefully I showed how a computer could reduce your Boolean or your gates down to a sum of min-terms, which would give you the numbers. It could then put that into a grid. What's the answer here? Oh. We want to simplify this. We could write the term for each one of these out and or them all together, right? We could.
Or
Well, the middle
Or,
one is Z.
right, so the
Yeah.
Z, we got the Z. That's
Z
where it's-
or
That poor
X
guy.
naught
Or-
Y Z naught.
That's why. X naught, Y, Z naught.
Okay, hold on. We could do X naught, Y, Z naught. That would technically be correct.
Yeah.
Oh.
But could we simplify this guy even more?
Yeah. Should it just be X, Y, right?
X naught Y.
X
Right.
naught, Y.
Because we can go ahead and highlight these two guys, and that's fine. I mean, if we, yeah, that doesn't mean anything. It's not like this is a super one, and that means something different.
Super one.
Da, 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 da.
It's exactly, which is just fine.
Everything's fine.
All right. So we got Z, and then we do X naught Y. Did I write that down? Great.
Wow, you're so smart.
Oh, okay. Now we need to do the
Whoa.
3-variable K-map for this. Let's go ahead and. Hey, look, I'll write this right here.
Whoa.
What? Oh, you're just over writing it.
That way
That
do
Y
it.
looks like an X on top.
Yep, it is.
That's
Going to
okay.
critic. All right.
Well, when people
Now let's see if
can't
y'all
tell.
can remember.
0, 1,
So which ones? So this guy is a
Oh,
1.
1,
0.
1, 0.
Nice. Why is that one 0?
Because that's the 3 1.
That's the 3. Because if you actually, yeah. Okay.
Yeah.
Or if you think about it, is the X naught, but then you have the Y turned on and the Z turned on, which makes it 3.
Right. So that's 1, 0. No, 1. Sorry, my bad. I lied.
Hold on. No, you're right. Isn't this a?
That's 4. That's 4.
4, 5, 7, 6.
Oh,
Yeah, I thought that.
0 1. So this should be a 0 then.
1, 0, 1, 1.
Okay, hold on.
That one should be a 1 because it's 0, 1, 3, 2.
There we go. That makes sense. So this is the 4. Good.
Right.
This is 0.
5, so 0,
1, 1.
1, 1.
So this is actually a 7. That's a 6.
6.
Great.
Yes.
All right.
Magic.
My bad.
Okay, now we got
I
that.
got thrown off.
What are we gonna do?
Group.
Do. So you got Z naught? Or no, it's Y naught, Z
Yes,
naught?
you got Z naught, which would get those 4 over there, wouldn't it?
Oh, hey, yeah. Go me.
So what's missing?
2 more.
2 more.
Okay. You got
Z.
No, you can't.
X naught, Y
Because
naught.
these zeros are here. You can't just write
Oh,
Z.
yeah.
X naught, Y naught.
Let's see.
The top
We
left.
got X naught, Y naught, so that'd be these 2 guys. All right.
Yeah. And then Y, Z.
And then
No.
Y.
X, Y.
X, Y. That would be these 2 guys.
Yeah.
Can
Okay.
it just be Z naught?
Oh, wait a minute. Okay.
And then Z naught got all the rest of them. And we got all of them? Yeah, we got all of them.
Woo.
Okay, the first one's the X naught, Y naught, has got that,
These 2 blocks right here. If you double up, that's perfectly fine.
Oh, okay, gotcha.
Yeah, doubling up's not a problem.
What about tripling up?
That's perfectly fine. You can add as many boxes as you want. It's good.
So theoretically,
Okay.
Any
Box
others?
Inside a box inside a box.
All right.
yes.
All right, now for the 4 variable.
Ah.
Oh, fish.
All right, this
Fish.
is as high as we're gonna go because going 5 variable gets confusing.
Why is there a fish?
A fish.
There's a fish because there wants to be a fish.
I don't know why he drew the variable order here. I don't know what he's
What
trying
is-
to do here. But
What kind of
So on
variable
this
order
one, you
is
need to
that?
have a block of 8.
yes, you have to have block of 8 because there's 4 variables.
It's-
Or
Whoa,
actually
that's
16.
16.
Sorry.
4 by 4.
It's 4 by 4, so 16
I
blocks.
don't
You have to have a
like
block of 8 to get just a single variable.
You got it, correct. If you had a block
Ah.
of 16, the answer would be 1, of course. So a block of 8 to get a single variable.
it. Oh, my head hurts.
Remember, these are midterms, so the 0 has to be knots on everything. The first thing to be turned on is the last one, which is Z. And then, oh, so he's having,
Oh, I'm
He's having W be the first
so
variable.
W is being the first variable here. Okay, fine, we'll roll with it. So notice it now goes 0, 1, 3, 2, okay, makes sense, 4, 5, 7, 6. What's that?
She said we're not round.
We're not
Let's
around.
roll with it. And I was like, but we're not right.
Notice that as we were flipping these 2, you also flip these 2, and that hopefully should make some sense because I'm going to write the bit representation of these 2 numbers in the
Oh, okay.
boxes. And now I'm 0, 0, 0, 0. You go down. Which bit's turned on?
4. So that one.
Yes. And then the 12,
Okay, yeah. Got you.
and then this final 8 is
1, 0, 0, 0.
Are you just writing the binary representation of those numbers?
yes. To show you
It all
how the
makes
bits are
sense
being
now.
changed. All right.
Because if we did it the other way, then you'd be turning off one and turning on one at the same time.
Yeah, you can't be
do
doing that. Not in this. All right, so
Not okay.
as you point out, a single variable has 4, or a single box has 4 variables, 2 ones or 3. 4 ones is going to be 1 variable, and then if you have 16 ones, it's 0 variables, aka the constant 0 or 1. Sorry. You good?
Yeah.
Okay. So which one is this?
There's going to be 2 variables.
So it's
Oh boy.
XZ.
XZ.
XZ. Everyone see that? Got all of X and then Z. There's their intersection.
Magic.
How about that one?
Wow.
Y, or W, not Y.
Yes, W naught Y. W naught and Y. Remember, it's really a W naught up here.
This is interesting.
Can we write those in? Because it's kind of like a little hard to
Sure,
see.
go ahead. Yep, feel free to fill this out as much as you need. And
The
then,
X knots. It's X doesn't need the knots up there.
X doesn't count.
Wow.
X isn't a real variable.
all right, how about those 4 corners?
Ah,
Aha!
no.
X naught, Z naught.
Let's see, X naught, Z naught. Yep,
Yeah.
because it's the X naughts and those guys, and then the Z naughts. Those intersections are the
Bingo.
corners. Thanks. Bingo. All right.
Bingo.
And then they decided to make it really
What?
confusing. We're
they
gonna ignore
didn't, they
that.
didn't make any of the other ones disappear. How are we supposed to see that?
Yeah, we can. Okay.
Let's play bingo with our tables. We'll be okay.
That's not going to help out here. Yeah, this is just confusing.
Oh.
All right. So in other words, if it was
All of
just
them.
this row in the middle,
All of them are
X.
chosen.
these two rows, sorry,
It'd be
these two
X.
rows, then it'd be X, right? If it's these two columns, it's
It'd be
Y.
Y.
If it's this row down here, these two rows at the bottom, it's
W.
W. And then let's say it's these two columns on the edges, it's
Z0.
Z0. All right.
Bingo.
I think
Slide
that's
fifth.
Pretty self-explanatory except for the four corners. That's X, not Z, not.
Yeah. All right, let me go ahead and draw this out for y'all.
Yeah, let's.
Copy pasta.
Yeah, I'm going to copy it.
You're gonna paste it on the board.
Yeah, I'm pasting it on the board. Isn't that amazing?
You have to do that primitive thing called writing.
I know, it's killing me.
You forgot the right side of the box.
Yeah, I can't even tell where
The
your
right
lines
the
are.
right line of the box.
Well, we're about ready to find out what I got right and wrong.
Oh,
Like I said, the right line of the box. There's just no edge.
Infinite.
All right. And we want this. Whoops. These will help us out. Okay, great. This one.
1,
All right.
0,
All right.
0,
Yep.
1.
No.
Yes.
Yes.
It's a 2.
Yeah,
It's
that's a
2.
Two. Thank you.
1.
1, 1. That's all the way
Or
across.
Yep, that one's all ones.
0.
Yeah, because this is 12, guys.
Yes. 1,
Yep.
1,
Mm-hmm.
0.
Because that's 12, 13, 15, 14.
Yes.
Now we go back to 8.
1,
1. 0.
0, 0, 1.
0, 1.
So just like you switch 3 and 2 on the rows, you switch
Yeah.
3 and what?
Remember when I was showing you the binary?
Yeah.
Yeah, I was trying to show you because we're only flipping one bit on or off.
You're flipping the third and fourth.
Why not?
Yeah,
X
yeah, over
is
on
the
this
one
side,
line.
yeah.
That is strange.
It is strange, but then it makes it very pictorially easy to see what's going on, right? Okay.
Okay.
So, what can we do to simplify this? Actually, do the slides
Why
tell
not
me?
X?
Nope. Okay, great.
Give up.
Why not X?
All right. Y.
Not Y, sorry, W not X.
W not.
X.
You got an X.
The one whole row there across.
Oh, okay. W not. Oh yeah, this is where it starts getting a little complicated. So we can do W not Z X, right?
You've got a
Yes.
XZ block in the
You
middle.
also have an X knot.
All right. So we're gonna do W not. Hold on. W not X. So that's this guy.
You just need another marker.
That
Thank you. No, that's good. Good comment.
Just different color.
to help make it
Hopefully this
stand
isn't too.
out. Hopefully it's not a permanent marker.
I think the permanent markers over there. That's their own fault.
That was funny.
Really?
Where's your other markers?
Bring
Nope.
them.
You know, I just need to throw it slightly more. Let's see if brown works.
Oh,
Ew.
of course it does.
Thanks, Caitlin.
No one wants to use that one.
All right.
You got the four corners. That's X.
Yeah.
X not
Oh
Z.
yeah.
So that's. So I gotta use the other marker
Play
now.
four corners.
So that's what you said.
Bingo.
X naught.
Z not.
That's correct, right?
And
Get yourself a Z.
oh yeah, and then you just need
And
the
an X.
The X naught, Z naught, and then X.
the
All right.
XC.
So what's left?
XC.
XZ.
Yep. So that's X and Z.
Whoa.
Wow, wasn't that nice? We just went from something. If we wrote this out, does anyone want to write this out?
No.
No. Okay, good.
No.
We went from oh no to oh okay. That's
Oh,
not
you
that
know.
bad.
So
3 terms.
you got 2 left, right?
Oh, I'm sorry. I didn't draw this
In the middle of the third. Those 2 right.
because that's what the XZ does. It got these 4. It got those 4. It overlapped with those 2, but that's perfectly fine.
So you can overlap. You can
Oh
use
yeah,
the
you can
full-
overlap whatever you want. It's not like one becomes a bigger one
You
or
can
something.
triple up, you can quadruple up,
Yeah.
you can quintuple up.
Because 1 or 1 is still 1.
I don't know what it is past that.
Okay. So, what's the literal cost of this?
What's the literal cost?
Mhm.
6.
6. Bring this back, right? So that's literal cost is 6. What's the gate input cost? Well, hold on. There's a gate another. I'm sorry. So they go in here, and then you got another 2 on this side. Because these literals go directly into a gate, so it's those 6. And then you're going to have another OR.
So 2, so it'll be 8.
Now remember, there are actually 3 going into here.
Right.
Because the answers to these 3 are going into a final OR.
Okay.
So
it
it's
is
actually
9.
another 3, which would make it
It'd be
9.
9.
And then it'd be 12.
12.
You have 3
Whoa.
knots, right?
For the
Okay, so
knots.
if you're doing the gate knot, then it would be 12, right?
Yes.
Right, so,
Because you add the knots as another gate.
This is what I did.
Yes.
So could you just do it whenever like 2 variables are together, that's a gate? Or
Yes. Well, because we don't write it, but there's really dots right here, showing you that these are ANDed. Okay. So which circuit's better, this guy or writing all that out? This guy, right? By a lot. Yes.
I must have missed that coming in the beginning, but then, okay, so literal cost is the actual,
How many literals do you have?
and then when you went to gate cost, or gate input costs?
Mm-hmm.
Um,
That's the input to all the gates. Now, you're using a literals, all your literals are going to be used as gate inputs.
Right.
Right? So you have those 6, then you just need to add what extra inputs are coming out of certain gates that are going to other gates.
And
So
two-
these ANDs are each producing another input that goes into a final OR. So there's an extra 3 gate inputs that are not
1,
literals.
2, 3, it would be 4.
Why would it be 4?
You said they're ORing at the
So we got-
final one's an OR.
So we have an AND, an AND, and an AND, right?
Right.
For these 3 guys.
All going into a final OR.
And these all go into a final OR. So the gate input cost is technically 1, 2, 3, 4, 5, 6, 7, 8, 9. It just happens to be that these over here are first your literals, and then you have an extra 3 coming out over there.
Gotcha. So 3 groupings give you 3 inputs to the OR.
Yes.
Okay. And what was 12 then, when you put the hell?
Oh, when you add the knots. Sometimes a knot needs to be calculated into the cost. So, because remember these knots, you're having the W come in, but you got to knot it as well, right? So there's an extra cost to that knot.
Yeah.
So you're just adding the number of knots you have. That's it.
So we do need to add that then, because it
For
are.
well, you have 3 costs. You have your literal cost, which we just talked about, the gate input cost, which was up here, and then your gate input knot cost, which is your gate cost plus all the knots you have. So these are 3 separate costs. Depending on what you're doing, we'll depict which of those 3 you use. Okay, let's do it again. This is on your homework, guys. That's why we're doing this.
I actually kind of like it. It's fun.
Is this all our homework is?
Yeah, also some midterms, max terms, and stuff like that.
That's okay.
Is that
Stuff
all
like
we're
this is
having
fun.
for this week then?
Well, I mean, we do have another class on
Well, I mean,
Wednesdays.
yeah, I didn't know for, are we?
On this homework, yes.
Okay.
What? There's more class?
Are we getting
I
assigned-
know you've gotten used to just 1 week, 1 day a week, but this is
We have
2 days a
multiple
week.
days of class this week. What is this?
Well, are we also getting a
School?
lab then too this week?
We'll probably. We'll
Lab
get
is
one.
due Wednesday.
We may get one on Wednesday. We may have to push it to Monday. Yeah, we got really messed up due to the
Snow day.
SNU day and then MLK day.
Snow day.
What did I say?
Are we gonna have another snow day?
We may. I don't know.
Supposedly.
Supposedly.
In February, we might.
All right, let's go fill this out. First
Okay.
one.
0, 0, 1, 0, 1, 1, 1, 0.
All right, does anyone? Okay, she's going really fast because you've got it. You
Yes.
obviously got it. All right, so
'Cause this is fun.
someone besides Sydney,
Alright, so what's up? 0, 0, 1, 0.
because that's the 3. Then we got 4, 5, 7, 6. Which one's this?
That's 10, right?
12.
12, 1,
1, because that's 13.
1,
15. 14. Now we go back to 8, which is
0.
then
1,
9. We're 9.
0, 0.
0, 0.
Yeah, 0. Okay, great.
That's easy. So you got an X, Z right there.
All right, yeah, picking out the easy one. So we got XZ. Oh, why did I get rid of this marker?
Why not W?
All right, we have Y naught W, which would be these two guys, right? Yeah, so we can do that. I don't know why I did W naught. We'll do W Y naught. And that
Also
would
have a W.
Whoa.
Wouldn't that be WY not Z?
be, yes.
Yes. Good job.
Good job.
And then you have a W not X.
So W naught X Z would be this, or yeah, these. No?
No.
Hold on.
That'd be W dot Y dot X.
Right. Yeah, and then that'd be these two guys.
I was trying to do all three. I don't know how to do that.
Yeah, well, you can't include that zero. All right, and we got this lonely guy up here.
You got two actually. One on the right side as well.
Oh yeah, we got another one right here. Wow.
W.
Okay, so we'll do W,
X.
W X,
Y.
Y. I think that's it, because you have the Z and the Z naught. So
And now you got the last one at the top. Now there's a lonely guy at the top.
Now we have the lonely guy. All right, and what's that last guy up top?
W naught.
Y Z X naught.
Y.
Then you cancel out the X's. So then it would just be
Y Z. Yeah.
W.
Oh, W Y Z.
not.
W naught Y Z. So W naught Y and then Z.
Yeah.
Yes.
Okay. People at home, there's basically no way for me to show you this. I'm sorry.
Good luck.
Yeah. All right, everyone.
Look at the previous slides because those kind of help a lot.
Yeah, they will help.
Do you want?
Yeah.
Should we do the cost like we did last time?
Do the website?
The cost.
Cost.
Oh, sure. Let's do the cost.
Literal cost.
All right. What's
Okay.
the literal cost?
14.
1, 2, 3, 4, 5. I haven't calculated yet. 6,
Well,
7,
there's
8,
4
12,
sets of
11.
3. Or
Well, then there's a 2.
4
right?
sets of 3 and then add 2. So it's 4 times 3
14.
plus 2
Oh,
is
yeah.
14.
Let's do actual math.
Oh!
Wow. Okay.
Snarky.
Yeah.
So,
And then 3, 4, and 23.
19 and 20.
Okay, we got 23.
That's
Wait.
for the
Oh,
knots.
that's for the knot.
Oh, no. Which one's for Gabe? Sorry.
19.
19. I got 19 as well.
Yeah.
And then
20.
yeah.
And then that's 20, 21, 22, 23. Yep.
So you add a cost each time you have to knot a variable.
For gate not. Only for gate not. Before, because normally you ignore the knots because it's such a cheap operation.
Okay.
But every once in a while it's important, so that's why it's a separate cost.
Every once in a while.
All right. Any questions on this? All right. What's coming up next? All right, good. So let's pause the video now.
That's a great way to end the video.
What?
I just asked her, did you just say